So we'll do an introduction to transformers and compare them largely with the recurrent neural networks, which was the previous dominant set of models in various applications in NLP, as well as a few vision applications like image captioning and so on, right? And now a lot of them have been replaced by transformers. So that's what we are going to talk about today. So to motivate, right, what is the content today going to look like, right? So we have seen three types of architectures. One was the feed-forward neural networks, then the convolutional neural networks, and then recurrent neural networks, right? And in each of this, we saw the building block, and then once we understood the building block properly, we could envision deep, wide networks, right? So in the case of feed-forward neural networks, the building block was essentially this sigmoid neuron, right, or any nonlinear neuron which used to take a bunch of inputs, do a weighted aggregation, and then pass it through a nonlinearity, right? So that was the basic building block, and then we had many of these connected in a layer and across layers to get a deep and wide neural network, right? Similarly, in the case of convolutional neural networks, the basic building block was the convolution operation and maybe even the max pooling operation. Then in the case of recurrent neural networks, the basic building block was this recurrent equation where you could compute ht, which was the state at time t, as a function of ht minus 1 and the input at that time step, right? So this is what the basic building block was. And then we saw the attention-based recurrent neural network, where we had the attention function, which was like a basic building block, right? So I'm calling these basic building blocks because if you understand these, then it's not very difficult to understand the full network, right? So similarly, today we'll focus on the basic building blocks of transformers, which is largely the attention, the self-attention and the cross-attention layers that it uses, and then try to relate it to what we have already seen in attention-based models in the context of recurrent neural networks, right? So that's the idea. So with that, let's zoom into the RNN-based models and just see some limitations of it, right? So one challenge in RNN-based models was that if I'm looking at the use case of translation, right, then my input is I am going home and I want to produce its translation in the target language, right? Now the input is given to me at one go, right? The input is not like coming to me one word at a time, right? I just tell the machine, hey, this is the sentence that I want to translate, right? But the computation is not happening at one go, right? So let's see what I mean by that, right? So what happens here is that you get the you have the initialization vector, right? And then you have this word I, and then you pass it through the recurrent neural network. So what you have here is, say, the embedding of the word I, right? So let's call this as x1. So this is the first word, so you have the embedding of that, and then what the output is h1, right? Or what you're computing here is h1, which is a function of h0 and x1, right? And now once I've done that, this h1 then becomes an input to the next computation, because h2 will be computed as h1 comma x2, right? So let's see this in the figure now. So I have h1, I compute h1, then I get the next input, which is enjoyed, right? It has some another sentence, so I think it's I enjoyed the movie Transformers. So I got h1, and now I use that and h1, right? So essentially I'm using this function, which is h1 comma x2, to compute this hidden representation or this yellow representation that you see here, right? So what is happening here is that my computations are happening sequentially, although my input was given to me at one go. I had the entire sentence at one go, and now let's just get rid of some of these annotations and just see the whole thing, right? So I had the entire sentence, and I'm still computing it one step at a time, right? I computed h1, then h2, then I'm computing h3, then h4, and so on, right? So I'm just doing all of this one step at a time, although this entire sentence was available to me right at the beginning, right? So now the question is, what's the benefit of what is happening here, right? So why am I computing h2 only after I have looked at h1, right? So the reason for that is that I know that for every word I already have the word embedding, right? So that's what my input is, and this word embedding could be computed from your favorite algorithm like word2vec or fastx or glove embedding, or it could just be randomly initialized. It could just be a learnable parameter in the network, right? But that is that is the embedding of the word computed from a corpus. But I want to know the embedding of this word in the context of this sentence. So that's what these yellow boxes are allowing me to compute, because they are taking input from the rest of the sentence, right? Now you might ask, hey, I'm only taking input from one side, right? I am not really considering transformers when I'm computing the yellow box for movie, right? But there are also something known as bidirectional RNNs or bidirectional LSTMs, where you start from right to left, right? So this is how the computation proceeds. For all practical purposes, you could think of, I have one sentence, I enjoyed the movie Transformers, so I computed these yellow boxes the way RNN does it. Then I reverse the sentence, so I feed in Transformers movie is the enjoyed I, and I again do the computation and then again compute some other, say, green boxes, right? And now I have two representations for every word. Say movie, I have one representation computed from the forward direction and another representation computed from the backward direction, and I could just simply concatenate those two representations to get the final representation of the word movie, right? And the reason I am doing this, or reason I am computing this one step at a time, is because I am interested in the context of the sentence, right? I want a contextual representation for the word movie. So that's why I was doing this one step at a time, to get the contextual representations for every word in the input, right? So which is also aware about what is happening in the words around it. So this is important, right? So the contextual representation is important. What is not good is, in the interest of doing this contextual computation, I'm not being able to do a parallel processing. I have to wait every time one word at a time, which is significantly, which reduces my computational efficiency, right? Because I'm just doing things sequentially, right? So now my wish list would be to be able to do this, to get the contextual representation. That means when I'm computing the yellow box for the word movie, I want to know what is happening around me. I want to take inputs from the other words, and right now these inputs are flowing through these hidden representations, H0, H1, H2, H3. So I want that to continue, right? And of course I'm doing bidirectional, so it's flowing from both sides. So I want that to happen. I want to take the inputs from all the surrounding words, but I don't want to do this in a sequential manner. I want a model which is not recurrent in nature, because the idea behind a recurrent equation is that you do something at time step t minus 1 and then feed it as input to time step t. So I don't want that to happen, right? So that's the basic problem I have with these sequence to sequence models, which I would like to overcome, right? And problem as well as a good thing. A good thing is that I want contextual representations. The bad thing is I don't want to do parallel sequential process, right? And once this is done, then you have the entire decoder block, right, which then takes in the final representation. So ignore this. For some reason this S2, S1 is showing up on the slide. It's not supposed to, but it continues to show up. So this is the final state, and then it's passed to the decoder, and then the decoder again does this sequential processing, right? And there, of course, I don't have much of a choice, because I produce the first output, which, say in this case, is none, and then that has to be fed to the next state anyways, right? So at the decoder, this processing will still happen sequentially, because I need to know what was produced and then feed it as the next input. So unlike here, where the entire input was available at one go, here the input itself, right, is being generated one step at a time. So I'll have to do sequential processing, right? But in the encoder, can I do something to speed up the computation, is what my question is, right? So we'll go towards answering that question, okay? So this is for the decoder, where I'm doing one word at a time, okay? But in the traditional encoder decoder model, the problem is that I just do this computation once. I have computed this H1 to H5, and then I take H5 as the my final representation for the entire sentence, and then this is the only thing which is fed to the decoder, and then the decoder just produces the entire output based on this one representation that was given to it. There's no notion of alignment, right? So there's no notion that when I'm producing none, I should actually focus more on I. When I am producing a transformer, I should actually pay more attention to transformer, and so on, right? So that notion is not there, and you know where that notion comes from, or what kind of models have that notion, and that is the attention-based models, right? So in the attention-based models, I have that, where I compute the RNN encodings, right? And now I'm just going to look at it a bit differently, right? So once I have computed this, once I have computed H1 to H5, now I don't need the RNN block. I just need these yellow representations that I have computed, which are the H1 to H5, right? So I can just take them out, and those can be my, those are now with me, right? So I don't need to do any further computation on these, right? And once these 5 blocks are available to me, right? So I've just made a copy of those representations and kept with me. sorry, the network seems to be, so once all these vectors are available, I can just throw away the encoder and just have the output of the encoder, which is these 5 vectors in this case. In general, it would be capital T vectors, where T is the length of my input sequence, right? So that's what I'll have. Now once I have these, I'll feed these as input to the attention mechanism, right? And this is what the attention mechanism does. At every point, it now feeds a contextual representation to the decoder. So it will just compute what is the most important word at this point, right? So you start, okay, go, start computing the output or start building the output. So it will just take a weighted representation of all the inputs to compute the contextual representation, which is just going to be like a attention weighted sum of the inputs, right? So that's what it's going to be. So I have these alphas coming in here. Sorry, for some reason the animations are showing up very slowly. Yeah, so I have these alphas showing up here, and then I take a weighted sum and I compute this contextual representation C1, right? So this is called the context vector. It's also called the thought vector. And for the rest of the discussion, I'll typically call it the context vector. If I'm calling it something else, I'll let you know at that point, right? So just think of this C1 as the context vector, which is a weighted sum or the attention weighted sum of the inputs, right? So you have just taken the outputs of the encoder, which were these yellow representations, which are context aware representations, and now again to the decoder you are feeding a contextual representation, which is, now here the context is basically where am I on the output. I'm producing the first word, so what is the most important set of weights, or what is the most important words that I need to focus on, right? And then you keep doing this at every time step. So you could think of is that you had this H1 to H5 weights, and then you are multiplying them, the H1 to H5 vectors, right? So you can think of putting them in a matrix, and then you have this vector of weights. So now you are doing this matrix vector multiplication, which is essentially taking a linear combination of all these columns, right? So alpha 1 1 into this, alpha 1 2 into this, alpha 1 3 into this, and so on, right? So that's the operation that is happening here, and then you get the you feed it to the decoder RNN, which then produces a output at the end, right? And you keep repeating this at every time step. You do it at C2, then you compute C3, C4, C5, and so on, right? So you keep doing that. Now what I'm showing here is what is known as a heat map. So this is what you typically look at when you are using an attention based model. So this has this is say a T1 cross T2 matrix, where T1 is the length of the input and T2 is the length of the output. Or the other way around, whichever way you can look at it. And now in this, wherever you see a light spot, that is the place where the attention weight is maximum, right? So when I was generating I, my attention on nan was maximum. When I was generating enjoyed, my attention on Rasithin was maximum. When I was generating fill, this was the maximum weighted word, and similarly here, right? It makes sense because these are almost like one-to-one correspondences in the translation output, right? So that's what the heat map shows you. Yeah, so this is how the heat map relates to what is happening in the sentence. As I said, that when I'm using nan, the maximum attention is on I, and the color coded, you can understand the colors here. So this blue color I'm focusing here, and this is the corresponding weight and so on, right? And you have some attention function, right? And we had seen this function. So you used to compute the attention weight, right, as some function of the previous state of the decoder and the input vectors that you had. So this was the attention to be paid to input I at time step t, which depended on the state of the decoder at time step t minus 1 and input I, right? And then you had this softmax function to make sure that this alphas formed a distribution, right? So they summed up to 1, right? So that's what we have seen, and you can use any alignment function here. We had seen one specific function in when we were discussing recurrent neural networks. So just showing the alignment function again, right? And here's a question now, right? So, and this is what will lead us to our eventual discussion on transformers, right? So can alpha ti be computed in parallel for all I at time step t? So what is the question that I'm asking? So I'm at a particular time step, say I'm at time step 4, right? So I'm asking, can all these alphas, alpha ti and t is equal to 4, so I'm asking whether alpha 4 1, alpha 4 2, 4 3, 4 4, 4 5, because I can take values from 1 to 5, can they be computed in parallel, right? And the answer is yes, right? Because this only depends on st minus 1, which is already available, and on hi, which is already available, right? So it depends only on these two values. So you can compute this in parallel, right? And of course, for normalization, you need all the values, but you can compute the scores in parallel, and then once you have the scores, you can again compute the normalization in parallel, right? So for a given t, you can compute the alpha ti's in parallel for all i's, no matter how many i's you have, right? So no matter how long your sequence is, you don't need to wait on the previous computation to happen, or to have something happen at I minus 1 to be able to compute alpha ti, right? You can just compute all of that in parallel, right? Now the other question is, so the main takeaway here is that the attention can be parallelized, but now the other question that I have is that can you compute this in parallel for all t's, right? So I said that at a particular t you can compute it in parallel, right? Now I'm asking that suppose there's this time step phi also here. So can I compute alpha 4 i's, right? All the alpha 4's and all the alpha 5's and all the alpha 3's, right? So all these alphas across different t's, right? So my t is changing here. Can I compute them in parallel? A given set of values, all the alpha 4 stars, right? Alpha 4 1 up to alpha 4t, I can compute in parallel, that we have already seen. But can I compute all of these in parallel at one go? And the answer is clearly no, right? The reason is that it depends on st minus 1, right? So unless I have computed st minus 1, I cannot compute any of the alpha t's, right? And st minus 1 actually depends on alpha t minus 1, because that's the input, right? So st minus 1 here, this one would depend on this would depend on C3, and C3 in turn would be a function of alpha 3, all the alpha 3's, right? So unless I have computed alpha 3, I cannot compute C3. Unless I have computed C3, I cannot compute S3. Unless I have computed S3, I cannot compute the alpha 4's, right? So all the alphas cannot be computed in parallel, but for a given t, the alphas can be computed in parallel, right? So now the two things to notice here, right? So one is that the attention can be parallel, at least at a given t it can be parallelized, right? It cannot be parallelized across t's, but for a given t it can be parallelized, right? And this is something that we would like to exploit and see that if we can get rid of this recurrent connection, right? Because this recurrent connection is still a problem for us, right? Because of the recurrent connection, we have to do things sequentially. But if we could get rid of the recurrent connections and then rely on the fact that the alphas can still be computed in parallel, then can we get to an architecture which allows us to compute these alphas in parallel, right? So it's still a bit hard to visualize where we are headed, but just keep these questions in mind along the way, and once we reach there, all these questions and the answers will make sense. So just to summarize the discussion so far, right? So I mean, everything about the RNN model is good, right? So what do I mean by that? We saw that across papers, right? I mean, we saw the architectures, they are used for machine translation, summarization, video captioning, image captioning, right? So they gave very good performance in a wide variety of tasks, right? But the only issue that we have is that given a training example, we cannot parallelize the sequence of computations because each of these guys needs to be computed one at a time, right? I cannot compute all of them in parallel. Of course, on top of that, if I have attention at a given time step can be computed in parallel, right? So now our wish list would be, can we come up with a new architecture, right, that incorporates the attention mechanism and also allows us to do things in parallel, right? So we don't want to get rid of the attention mechanism because the attention mechanism helps us to compute the contextual representation, but we want parallelism. We also don't have a problem with the basic idea of recurrence, right? That the recurrence actually allows us to compute things which are contextual, right? So we don't have a problem with this here. So we don't have a problem with this here. This is fine because this is allowing us to compute these recurrent or the contextual representations, but we have a problem with the computational cost which comes with recurrence. That's the problem that we want to solve. Okay, so that's the context. So that's a quick recap of recurrent neural networks and what we see as problems in the recurrent neural network, and now we'll try to go towards a solution for that, right? And that might probably lead us to a new architecture. So I'll end this video here and we'll come back and continue from this point.